We can start, and firstly I'd like to recall the Liouville-Arnold theorem. It's a very complex statement, so there are different aspects which are important for us in what follows. So I'd like just to recall the statement. So we are in the framework of some symplectic manifold. So thinking about general Poisson manifold, we should choose a symplectic leaf to be in the context of the Liouville integrable system. And so the dimension of M is 2n, and we need a family of function Hn infinity on M to be functionally independent. Functionally independent. And to be in involution, Aj is equal 0 for all H and J, I and J, and all this function should be, so there is a Hamiltonian which defines a Hamiltonian system on this symplectic manifold, and we also need that all this function be integrals. So we need maximally big commutative family of integrals of our dynamics. So this number is the maximal number of independent involutive integrals on the symplectic manifold. And in this, so this system is called Liouville integrable. So such a system is called Liouville integrable, and the following theorem describe why we are interested in such situation. So first of all, we consider a common level set of our involutive family of integrals. It is the subset of our manifold of the fixed values of all Hamiltonians. Ci. So this is in a generic situation, it is a submanifold of dimension n. But if we have a Liouville integrable system, such a level set is a Lagrangian invariant Lagrangian subvariety invariant with respect to Hamiltonian vector fields. Vector fields X, H, I.
Sorry, would you mind adjust the camera a little bit? I mean, remove the left to set.
Is it better?
Yeah, a little bit more now. Yes, yes.
Uh-huh.
Okay, thank you.
So, the fact that the subvariety is invariant with respect to the Hamiltonian vector field is obvious. It is the fact just because it is defined by the constant value of some of our integrals and in evolution. So in evolution, so we have to calculate something like this, hi, and it is the Poisson brackets of Hamiltonians, and it is 0 due to the involutivity of. Okay. So it is an invariant subvariety with respect to the Hamiltonian vector fields. It is important because we can restrict our system to this subvariety. It is the first step to simplify the system.
What is this X?
X, it is a Hamiltonian vector field defined by a Hamiltonian function. Do you remember? X of H is minus Pij dHj over I'm sorry.
Yeah, I remember, yes.
dxj d over dxi.
Yes.
J. So it's a vector field defined by the Hamiltonian function. It is the same. So in fact, it is the definition. Okay, the fact that it is invariant is simple but important. So it's the first step to restrict our to make the dimension smaller, the dimension of our variety. The fact that it is Lagrangian, so it's a general statement. You see the Hamiltonian vector fields of function hi, they are tangent to this subvariety, and they are independent. And do remember that if we insert Hamiltonian vector fields to the symplectic form, it is the same as the Poisson bracket of these functions, and it is 0. So these vector fields, they are independent due to the functional independency of Hamiltonians and due to the degeneracy of symplectic form. The inverted matrix gives us a Poisson bracket. So this Poisson structure is non-degenerate. It transforms one forms to vectors. And the functional independency means that the differential of functions are independent. It means that dHi are independent, are linearly independent in T star to M at each point. So this is the functional independency. And then we apply to them the Poisson bivector. We get R independent in tangent space to M, but so in fact they are tangent to HI, element of the tangent space. Okay, there are no needs to make it more precise. So they are independent in the tangent space to the variety M, And here we see that if we apply the symplectic form to such vectors, it is 0. So you see in the dimension, in the subvariety of dimension n, we have n independent vector fields, and the symplectic form is 0 on them. So it is 0 on all this subvariety. And
It's called subvariety. I mean, the word subvariety means what in a general sense? Here is a formalized definition.
yeah, it is given by a set of equations.
Okay.
Let us think about just a subset, but it is also a smooth variety at a generic point, at the generic point of C. We will see it on examples. So for the generic choice of C, it is a subvariety, so it's a variety of dimension n. And the restriction of the symplectic form on it is 0. So, and this is a definition of the Lagrangian subvariety. Okay, next, very important statement that we can choose coordinates, local coordinates HI and TI such that TI are times with respect to HI. See, it means that if we choose our level set and start to, so there are vector fields XHI, XHJ. So we locally we can solve these vector fields and introduce times which describe how a point goes along this vector field. So here the involutivity is very important. If they are not involutive, we couldn't introduce times as a coordinate. You understand? Because if we transform, if we make such a diagram, it's not the same point. So the fact of involutivity of such Hamiltonians and Hamiltonian vector fields, commutativity of vector fields, gives us good coordinates on the level set. It means that okay, there are such set of coordinates and dynamics Ti dot with respect to x h j is delta ij and obviously xaj applied to to h I is 0. So the statement about local coordinates, even if we change the level set. So it is this quantity describe local coordinates in some neighborhood of the point in the whole variety M. Okay. Next topological property of an integrable system. If MC is compact and connected, then MC is just an n-dimensional torus. One power n, the Cartesian product of a circle n times. So it's quite a strong statement, and so it can be understood in the following way. We have an action, so our set of Hamiltonian vector fields describe a local action of the Lie algebra, of a commutative Lie algebra. We can exponentiate each Lie algebra action to the action of the group. And so if our level set is compact, we have an action of the group Rn on the compact variety. So the typical next step is to analyze how can be what form could have an orbit of an action of the group Rn. And you remember that orbits are characterized by stabilizers, and in this case the stabilizers could be only the integer lattice. So an orbit in this case is Rn by Zn. And this is exactly n-dimensional torus. There are some subtleties how this action is organized. Is it discrete? Is the stabilizer act discretely or not? But it's the case. So that's why the stabilizer could be only the integer lattice. And such torus has canonical coordinates, which will be called angle variables, angle variables, just phi I, phi I a coordinate on S1, on the if copy of S1 in this direct product. So it's a coordinates which is periodic.
Yeah, for example, if I have S2, then it's like the 3 other angles of the sphere or something like that.
No. In the integrable situation, we always have commutative group, and that's why it's only torus. No.
No sphere.
No sphere. Okay, so these coordinates on S1, the number of such coordinates will be called angle variables of an integrable system. And the last and very important part of the Liouville theorem, that if MC is compact and connected as like as MC prime in some neighborhood for C prime in some neighborhood of C, a neighborhood of parameter spaces of parameter space, a neighborhood of C in the parameter space. So we fixed one level set, but we need to consider a level set near C.
Where is C here?
C, it's a set of values of Hamiltonians. So we need that the level set is compact and connected not just in one point, but in some neighborhood of values of Hamiltonians. A neighborhood of C in the parameter space. Then one could introduce action angle coordinates in some neighborhood of MC, which are I and phi, such that are integrals, means they are functions on HI. The functions on Hj phi phi dot are constants with respect to all x h j, and moreover phi are angle variables angle variables on all terrae in the neighborhood of MC. So you see, it means that we have a terrae which is MC, but there is some neighborhood of this terrae which contains only terraes of this torus, which contains only terrae. So this is MC prime, this is MC 2 primes, and the statement says that we can choose coordinate phi I for all this set of level sets, for all this family of level sets, homogeneous. You see, there's some set of torus, and we can find the angle variables just for all these torus. Moreover, the symplectic form in this coordinate is canonical. Phi, and these coordinates can be expressed in quadratures. Starting by the initial coordinates. do you know what does it need to be expressed in quadratures? To be expressed in quadratures. Means by operations the use of the implicit function. It means we can solve some equations. So you see, when we choose a level set, the theorem of the implicit function says that you can find locally expression of one coordinates in terms of other coordinates, just using the equation. Sometimes it could be very complicated, but it is implied in terms of to be expressed in quadratures. And then we can apply operations integration, and differentiation. It could be too general as the number of permutation, but so it's not the case for the chaotic system. In chaotic system, you couldn't express solution in quadratures. So the fact to be integrable specialize very strictly the physical nature and the behavior of the system. Okay, we will try to understand this definition on example. And the first example is the pendulum, but not mathematical pendulum, but a real one. So it is described by the equation, by the Hamiltonian, firstly by the Hamiltonian h 1 over 2 p square minus cosine of phi. And phi and p are canonically conjugated variables. So pi phi is equal 1. And so this means that phi dot is pi and pi dot is minus sine of phi. Do you agree? And that means that that phi is minus sine phi. Okay. So our space is just a two-dimensional space.
Is a momentum here, right?
Yeah. Yeah. Yes, of course. So it's two-dimensional Poisson symplectic variety. But what do you think? How it is? What is it? What is it as a manifold?
But is it as a
Manifold, yes, the phase space of our system. It is two-dimensional, and it is symplectic. So you see, we have non-degenerate Poisson structure on a two-dimensional something. But what is as a manifold? Is it R2? Okay, it's not R2. It is S1 over R. So phi varies only on
S1?
S1. Yes. So it's a cylinder. Something like this. So here is the coordinate pi, and here we have a periodic coordinate phi. Okay? I'd like to consider it, how to say, развертка. So here is phi, there's pi, p, 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 p. This 1, 0, maybe minus pi, pi, 0. So it's periodic, but we should consider only this band. In all cases, we have an integrable system because we have a two-dimensional Poisson variety or two-dimensional symplectic variety, and we have one function. So it's half a dimension of our space, and the Hamiltonian is integral. So it's an integrable system in this case. But its affiliation in inter is not trivial. So our goal is to understand how the phase space of our system is affiliated into the action angle variables, into this product of Toda.
So this quadratic picture is just a projection of this?
I have cut and how to say linearize this system, this space. Okay, so it's a value 0, and we have to consider the level set of our Hamiltonian, of our integral. Physically, you understand how it moves. So if we started at this point with the 0 momenta, it's a stable point. Okay, and this stable point means that p is 0 and phi is 1 is 0, and it means that h is minus 1. So my statement is that h is equal minus 1, so it's a level set. Let us describe it as m minus 1. It's a level set of our integrals with the value of an integral equal minus 1. Okay? There is another very interesting value of integral. It corresponds to this point of non-stable equilibrium. So it's the variety M1. So when this Hamiltonian equal 1, it means that at this point p is also equal 0, but phi is equal pi, and the cosine is equal minus 1, so h is equal 1. So I'd like to express the level set of this value. So it is. It looks like this this curve. It has singularity here. it corresponds to the fact that to reach this point, we spent an infinite time. But the rest of this variety is foliated inter I. So, for example, if we consider MC with C n minus 1 and 1, we get periodic orbits in this domain. You see, this all this set is just S1 cross R. I mean that this open interval is homeomorphic to R. And all level set are just circles, so it corresponds to some periodic trajectories in the phase space. And MC for C from 1 to infinity. From 1 to infinity, it corresponds to 2 copies of the same space. And it corresponds to such trajectories like this. And this corresponds to the rotation in one direction, because the momentum are always positive. And the same time, the trajectories of the same type, but in the lower half plane correspond to the rotation in the inverse direction. And these trajectories are also periodic. You see, this point coincides with this point, and they're like this. So, and all this family of level sets is also the copy of S1, but it's a particular case of a torus, and this is the family of torus. And the natural question in this case, and it is your home task, to find action angle variables for the pendulum. You see, it's one. So all dri are one-dimensional. So it's only one variable. But the Liouville theorem states that it exists a variable which is just the periodic variable along these orbits. So it could be obtained by quadratures, by some integration. Okay. So I would like to talk a little bit about chaotic dynamic and the KAM theorem because it's very close to the formulation of the Liouville theorem. So it gives some intuition about the role of integrable dynamics in all variety of other dynamics. So, but just some words in the statement of the KAM theorem. KAM theorem. So we have understood that integrable. So let H0 is an integrable, defines an integrable system, is an integrable Hamiltonian. So it means that there are always all these structures needed to define the foliation into Lagrangian subvarieties. There is a set of integrals in evolution, and we have understood that the movement is. So it's better to. So it's a Tarai. Tn. So there are many directions, but it is periodic in all directions. So we know that there are action angle variables d phi I, and phi I are just these periodic coordinates on Tarai, and I are functions on H1, Hn. Let it be. No, it is 0. It is 0. It is 0. So, so which H? So it's not very good. It is 1, but I need also 0 here. Okay. It is not so important now. And so we know that if we consider dynamics of phi I with respect to the action Hamiltonian, so let's apply xi to phi j, then it is just delta ij. Okay? Just because it defines the canonical coordinates on our Poisson and symplectic space. But if you consider the dynamics with respect to our chosen Hamiltonian of phi j, then it is defined by dh10 di delta ij. So even it is just this one. Okay. So we know that the variables h and variables I are just different bases in this subalgebra of integrals. Okay. So in the set of integrals, there is a basis h, and there is another basis I. So they are functionally independent. So they could be expressed. One set could be expressed in terms of another, and in the inverse sense else. So h depend only on I. So these are some functions, but these functions are also integral. So you see, these functions are just constants on the level set. These functions are constants on MC, on the level set. On the level set on our torus. And you see, it means that our trajectories of our physical system, which we explore, are just a quasi-periodic movement on the torus. Something like this. In this case, so this equation defines a quasi-periodic on Tn. One distinguishes the resonant and non-resonant quasi-periodic movement.
Is quasi-periodic?
Quasi-periodic means that so it could it means this movement. So there is no period. Yes, it's not periodic. It could fill densely all torus. It depends on the ratio of the frequencies. If it is not rational, the trajectory fills densely the torus. So it's not periodic.
Okay, yes.
So for the general choice of this constant, it's quasi-periodic, it's not periodic.
The thing that you have seen in the last picture, like that, right? You just get it
Yes.
dense.
No, the picture, all the movement was periodic.
Okay, last time.
There is no chances because the torus are one-dimensional. Understand? But if you have many directions, then the general situation is quasi-periodic. Okay, so definition. The trajectory is called resonant if the number of independent frequencies omega j over z is less than the dimension. So you see the general situation. So if we have chosen some integrable system, we have chosen Hamiltonian, and we constructed the Lagrangian tori for the system. In general situation, it is quasi-periodic and non-resonant one. So we have here just generic values of frequencies, and there are no integer relation between them. So this means that the trajectory, each trajectory, fills densely all the level set, completely the level set of integrals.
Just because it's densely, we are calling it resonant, right?
Not resonant.
Not
resonant. If
it's like periodic, then we call it resonant.
Yeah. So it's periodic, but of lower dimension. Okay. So suppose that only one frequency is non-zero, and all other are zeros. When we will get a movement just along one direction on the torus, it is resonant because it doesn't fill all the level set. Okay. So I'd like to formulate the KAM theorem, but in a very simple version. So we consider.
What is written in the definition?
The trajectory is called resonant if the number of independent frequencies over z is less than n. Independent over z. Consider a deformation of our integrable system of H10 of small order. So we have a Hamiltonian which is H0 plus stuff. And epsilon is small. And we can consider the trajectories of such system. So the statement theorem KAM. KAM, you know, it's Kolmogorov, Arnold, and Moser. It says the following, that you see, in the integrable system, the generic torus is non-resonant. So the KAM theorem says that if we deform the system, some invariant terrae deforms but stay invariant and stay topologically terrae. So the small deformation preserves some invariant non-resonant terrae. It means that they could deform but they stay invariant and with non-resonant trajectories. And there is a very important.
And then what is deformation here in this case?
So it doesn't stay just not really the same. Yes, they deform, but topologically they stay
and
torus.
What causes that deformation in the equation of motion?
Yes, the equation. You should think about the solar system. So if the interaction between planet is small, it's just a Kepler problem, which is integrable. But if we start to consider the interaction between planets, it became not integrable. But the statement is that some movement with quasi-periodic orbits stay the same. The orbits move a little bit, so they deform, but they stay quasi-periodic on some new subvariety. So the subvarieties, the non-invariant non-resonant, the invariant subvarieties, they deform, but the behavior of the system on these subvarieties stay non-resonant, quasi-periodic non-resonant. And there is some very important additional information in this theorem. It says that the measure of the complement to the set of invariant non-resonant tori is of order epsilon. So you see, if we consider small deformation to our energy, which describe the interaction, then the measure of tori, which are not deformed from the tori of the integrable system, is such small as the parameter epsilon. You see, this was an advantage of integrability context and of the action angle variables to apply to the solar dynamics. You see that it is not integrable. You see that there could be some behavior which is absolutely different from the integrable one. So the n-body system is chaotic. But this theorem says that if you consider its point near the integrable point, that the number of tori which deform in some resonant way, it is such small as the parameter of deformation. Okay? Very good. And now we proceed to some concrete example of an integrable system, which will be our subject for several next lectures, and it is the open Toda chain. It was invited in 1967 by Toda. By Toda in the context of solid physics. So it was the model to describe some processes in crystals, in one-dimensional crystals. And it appears to be integrable, and lately appeared to demonstrate some strong connection to algebra, geometry, and many other structures. So that's why it is an interesting example of an integrable system. So it is described on the standard symplectic on the standard symplectic space with coordinates pi and qi, with the canonical Poisson bracket delta ij, and by a Hamiltonian, which has a kinetic term, and the interaction is described by some exponential potential. Plus. And the equations itself is the following: EQi minus 1 qi eqi eqi plus 1. So it corresponds to some system of particles on a line q1, q2, qn, and we suppose that to define this equation, we suppose that q0 is minus. Yes, this is an equation of motion, and qn plus 1 is equal to plus infinity. So you see the interaction is described by this repulsive interaction between particles. So okay. So the first statement is that is to demonstrate that this equation of motion can be described by this Hamiltonian, but maybe it will be also the task.
So as I understand, this is a classical Toda chain, and there is also a quantum Toda chain or something like that.
Yes, but we always
described on this on a circle or something like that.
Yes, there are all there is all variety of Toda system, but we work principally with the classical system. So in the task here is that the equation of motion is Hamiltonian with the Hamiltonian function h. Okay. Let us introduce other coordinate flushka. Coordinates. A j minus bj bj one. I'd like to express all the things in flushka coordinates. So
sorry, in the first task, we need to show that, or what to do in the first task?
That
Just derive?
yes. Okay. So in flushka coordinates, the equation of motion takes such a form. G minus 1, 2, and bg. And the Hamiltonian is more symmetric. Square plus pj square and minus 1. You see, bj is defined, aj is defined for all j, but here j is from 1 to n minus 1. Okay. Let's try to do this calculation. aj dot, which is -1 over 2 pj dot. Pj dot is equal -1 over 2. We have to calculate pj dot, we have to calculate the derivative of this expression respect to qj, and we with the inverse sign. So it's 1 over 2 pj q j minus q j plus 1 minus e q j minus 1 minus qj. Do you agree? Okay. And if so, we have to compare with bg. I have an impression that it is equal. Okay. Yes. Bg square bg minus 1 square. Okay. So this is correct. And b j dot is 1 over 4 q j dot minus q j plus 1 dot, and it is equal 1 over 2 bj, and qj dot is just pj minus pj plus 1. And this is bj aj plus 1 aj. Okay. And now we proceed to a very important concept of integrable systems, which is called the Lax Representation. So we need to introduce two matrices: matrix L, which is a matrix n by n, with a variables on a diagonal and b variables on two subdiagonals, n minus 1, b1, bn minus 1, and zeros out of three principal diagonals. You see the Flaschke coordinate b, they vary from 1 to n minus 1, so it is very well arranged to the role in this matrix. And we also need matrix M, which is L plus minus L minus, but I will write it in coordinates. B1, bn minus 1 minus b1 minus bn minus 1. So this is the upper triangular part of the matrix L, and this is the lower triangular part of the matrix L, and this is the difference. Okay, so on the diagonal they coincide, so this difference produce only zeros. But off diagonal we have b plus, bi plus, and in the lower diagonal we have the same coefficients with the sign minus. The Toda Toda chain equation is equivalent to the equation L dot is equal ML. We mark the equation 3 is called Lax Representation.
The same equation also holds for Talalaif system and other systems.
Yes, yes, it's a very general phenomenon that integrable systems can be put into this form. So this is very deep property. I will comment it, but firstly we have to understand how to work with this, with such a representation. Let's look at this equation. So you see, we have introduced some metrics which depend on the point of our variety. So when the point evolves according to the Hamiltonian equation, the matrix evolves in some manner. So this statement says that the evolution of this matrix is described by some adjoint action of the Lie algebra of matrices. So this Hamiltonian evolution, which is described by some Poisson bracket, is the same as the evolution of matrices given just by some adjoint action of some matrix M. You see, this matrix M is also depend on L, and it means that it is also a point depends on the point on our phase space. Okay, just corollary. Traces of LK are integrals of motion. So you see, if you manage to represent the dynamical system in a Lax form, just always you have construction of integrals of motion. How to demonstrate it?
Maybe we can look at an example of this for the simple pendulum.
Yes, of course. Yes, of course. But it is simpler than when it's needed. Yes, yes.
Excuse me, sir.
Yeah.
I can follow how to introduce the L matrix. Could you explain?
There is no explanation. It's an ad hoc construction. So it is known that the system can be represented in this form. But we will demonstrate it now. So I couldn't present you an argument how to find the Lax representation. It's a very complicated problem. But if you have the Lax representation, you have many important properties of the system. For example, you have a construction of integrals of motion. But this also, it is not yet proved. I will provide some explanation and demonstration of this.
Like that. If we have some integrable system, then we can construct such a matrix from the integrable system, which is the L matrix.
If you have a dynamical system, it's a miracle if you can find a Lax representation of it. Because if so, you have many integrable properties of the system in some generic way. Okay, but let us proceed progressively. in this program. First of all, we have to demonstrate that the Lax, the dynamical system is equivalent to this form. Okay, maybe it will be the task. This theorem will be task 3. And I will demonstrate how the Lax representation influence the integrability.
So the task 3 is
to demonstrate this theorem that this equation of motion are equivalent to such an equation. But you understand what is written here. L dot is just the dot of all.
So in flash coordinates, you need to demonstrate this equation 3.
Yeah. So you have to calculate the commutator of such matrices and to show that the derivative with respect to Hamiltonian vector field is the same as the commutator of such matrices. But now I will comment this statement, which make a relation with the world of integrable systems, but not yet exhaustively, because I couldn't demonstrate for the moment that these integrals are an involution. But all such functions should be integrals. And it follows, okay, first of all, I'd like to calculate the derivative of Lk over d. It's a proof of a corollary. It is I should differentiate it by the Leibniz rule, but now L is an element with, so it's a matrix. So it's the following: it's L dot multiplied by Lk minus 1 plus L multiplied by L dot multiplied by L power k minus 2, etc. Lk minus 1, L dot. I'd like to write it as the sum over I from 0 to k minus 1, L power I, L dot, L power k minus I minus 1. Okay? In place of L dot, I should put the commutator. So it's a sum k minus 1, L I, L ML minus LM, L k minus I minus 1. And this is equal to k minus 1 L I M L minus I minus L I plus 1 M L k minus I minus 1. Okay. And now we have to note that these are principally the same summations, but with different set of indices. So I like to write it in the following way: 0 to k minus 1 L I k minus I minus 1 to k. L I M L minus I. In this summation, I moved the index I. I consider I plus 1. Okay? And this I plus 1 goes from 1 to k. But now all terms cancel except the boundary terms, so it is equal L I have to consider I equal 0 here and I equal k here. So it is M L k minus, and here I should consider only I equal k, L k M. You see? So it's a commutator of M with Lk. But now we have to consider d over dt of trace of Lk. And the trace is a linear function. It commute with differentiation.
Yes,
So is equal to trace of d over dt of Lk, because trace is a linear function. And this is the trace of M Lk, and it is 0 because it's a commutator. Okay, we stop. We make a break 50 minutes before our seminar part.